Hey everybody, welcome back to Young Engineers of Today, the amazing Mechatronics. So we're going to be we're coming up actually pretty fast on the last couple of classes, and we'll spend this time getting through basically the rest of this presentation. It's going to be a fair amount of stuff anyway, so we're going to get through it as quickly as we can, cover as much of it as we can, and hopefully we'll have some time left over for just general kind of stuff. I did Ved. I might actually, see if I can't get my loot boxes for that event. But yeah, so once again, we're going to be utilizing the GPIO pins, or the general purpose input-output pins, um, for the Raspberry Pi. And this time, no, it's still not working, unfortunately. I ordered a card reader, but it's not going to arrive in time. Which is just, it's not ideal, but I'm gonna try and hopefully find, I don't know, alternative avenues for connecting to this thing. Well, whatever, we'll see. Anyway, we're going to utilize the input aspect of general purpose input-output pins, because so far all we've done is the output, and we've just made it so that the Raspberry Pi makes, oh, thank you, Ved. Yeah, he says anybody who needs breadboard kits, Viabot is good. And that is spelled as such. Thank you. That's a helpful it's a helpful bit of information. But yeah, so far we've messed around with the output side of things, and we've seen that even with something like that, Raspberry Pi has the ability to uh, make the output more complex, which can be more useful. So for instance, having the lights blink in a specific way, or having the speaker, like if you could hook up a speaker to it and have the speaker output certain things, or as most people know them as noises, uh, some sort of structured sound, like it could be music or it could be a voice or something like that. It wouldn't be anything terribly complex because high fidelity speakers require quite a bit of power and also quite a bit of circuitry in order to get them to replicate things like the human voice and stuff like that. But you could do like an NES style speaker or an old PC speaker style thing. Um, anyway, that's something we could do with just utilizing the output aspect of it. Taking advantage of the input as well, suddenly the complexity of our circuits can, increase. We can not only have the Raspberry Pi give us intelligent output, but it can give us intelligent output based on the input that it receives. It can respond to the environment around it, whether or not that's temperature or ambient light or ambient sound, or something as simple as somebody pressing a button, which is actually what we're going to be doing for today. We're going to be messing around with a button. So that should be pretty interesting, hopefully. I'm going to go ahead and start this up in Fritzing so that I can show you guys the circuit setup and everything. And we'll give that some time to start up, because that'll take a minute. It won't be fast. Okay, here we go. So fritzing is open. Took a minute, but it always does. So I'm going to go ahead and go over to the breadboard side again. And remember, breadboard side by default has a breadboard. I'm going to go ahead and rotate it 90 degrees so it's vertical. This is just something that'll just make your life easier when you're working with breadboards in general. Obviously, if you're working with them in real life, it seems kind of odd for me to say, okay, orient your breadboard 90 degrees and that kind of thing, because you're going to be dealing with the jumper cables, and they're just going to sort of orient themselves however they may, and basically you'd set it up with the way that's the most comfortable for you. But on something like fritzing or circuits.io, when you're working with it later, because you probably will be working with it later, as in like next year or sometime in the future. Having it in a vertical orientation right next to whatever the microcontroller or microcomputer is, whether it's Raspberry Pi or Arduino or something like that, orienting them vertically next to each other is generally just kind of a good idea, because it lessens the amount of clutter that happens on the screen. So let me go ahead and, all right, pull up the Raspberry Pi. Give it some time to figure itself out. There we go. Rotate. Bam. So now I've got them right next to one another again. So all of my GPIO pins have easy access. And so far, so good. All right, so this is going to be a fairly step-by-step process. Actually, that won't be necessarily a terrible thing. So let's go ahead. I'm going to walk through this very explicitly step-by-step. So I'm going to take, in this case, it's going to be pin 11, which is GPIO 17. And I'm going to connect it to A4. I'll make it orange, just so we can discern it from everything else. But as you can see, I've got it hooked up to, if I mouse over it, it'll say GPIO 17. Over here, when I said A4, as we can see, if we're looking at this, all the columns are lettered and all of the rows are numbered. So when I say A4, I mean column A and row 4. And that's it. Just, follow the coordinates and hook it up there. So far, so good. We have our Raspberry Pi hooked up to the at least one part of the breadboard. And then I'm going to bring in an LED. Bam. And I'm going to bring in a resistor. Bam. The joint in the wire is not a necessary thing. I just made it so that it's easier to see. Like I'm not covering over any of the other slots on the breadboard or anything like that. That's something I did so that you guys can, it's not overlapping anything and it doesn't make it, more cluttered looking. This is not something that you, strictly speaking, have to do. The resistor is going to be a 330 ohm resistor, I believe. 330 or 340 ohms, whatever you have available. But yeah, so let's go ahead and hook up the LED. So let's see which end is the cathode and which end is the anode. This is the cathode and this is the anode. So why don't I go ahead and hook the, come on, cooperate with me. Hook the LED up so that the anode, yeah, we're gonna have the anode plugged into the power from the Raspberry Pi. And then we're gonna have the resistor, and let's go ahead and make this, we'll make it, I'll make it 330 ohms. If you have a 330 or 340 ohm resistor, it doesn't really matter. But I'm gonna make it 330, I'm gonna hook it up from the cathode on the LED, or the shorter leg, yeah, the shorter leg, to the minus rail on the breadboard. So as you can see, it's just jumping straight across. So I've got the LED plugged into E4 and E3. The anode is in E4 and the cathode is in E3. The cathode, oh, okay, so let's go ahead and pull that back up real quick. LED, anode, cathode. So the cathode is the shorter leg on it, which is kind of confusing because they're very similar names to anions and cations when you're thinking about molecules and atoms and things like that. Well, ions in essence. And the anion is the negative ion, whereas the cation is the positive ion. On an LED, the anode is the positive terminal and the cathode is the negative terminal. So it's backwards from those things, which is part of what screwed with me for so long, was thinking about it in terms of molecules and ions, but it's actually exactly backwards from that. So in this case, the cathode is the shorter leg. Oh, let's see here. I hooked up an LED exactly how you did it with my Pi, and the LED kept being lit. I checked the pins, and it was connected to, and they were correct. Hippo and ground. Oh, GPIO. Um, yeah, exactly. As it likes to do. Without being able to look at it, I couldn't tell you. My suspicion is if you're, unless you are absolutely certain it was hooked up to a GPIO, it might have been hooked up to power. If it was hooked up to a GPIO, GPIO 17 may be something that constantly sends out power unless it's been programmed by the Raspberry Pi to do something else. So if the, check your programming logic with the Raspberry Pi as well and make sure that it was set up to, turn on and off. Okay, well that could be it too, because let me pull up the pin diagram again. Well, let me just point it out on fritzing. Well, no, I guess. Well, here's the thing. This ground up here is right next to the 5 volt, and then the GPIO is right next to the ground. So it might have been, well, no, that would have made a short circuit. That wouldn't have actually powered the circuit. As it stands right now, from what you're saying, it sounds like your best bet may be to explore the scripting side of it and see what you had set up for it, just to double check that aspect. Obviously double check your circuitry as well, but like I would look at the Scratch scripting and see what exactly how it flowed and everything. Yeah. Okay, so yeah, we've got GPIO 17 hooked up to the anode on the LED, cathode on the LED, which is in E3, is hooked up to the resistor in B3, which is also hooked up to the ground rail. So just straight from B3 to the ground rail. GPIO 17 to A4 to E4 to E3 to B3 to ground rail. And then I'm just going to hook up the ground rail to the ground on the Raspberry Pi. And I'm going to make this a black jumper wire so that we know for certain that it is a ground jumper. And I'm going to hook up the power rail to the 5-volt power on the Raspberry Pi. We'll make it red just so we know for certain. So now we've got a complete circuit here, because since this resistor connects to the ground, and the ground is connected to, the ground rail is connected to the ground on the Raspberry Pi, and then the Raspberry Pi is also providing power. Now, you probably have also noticed that the power rail is not actually connected to anything. Like, we've got it hooked up to the power on the Raspberry Pi, but it's not actually hooked up to anything on this circuit. And that's because we're going to use that power rail in order to test and make sure a button works. I'm just gonna, be a little weird, but it'll make sense. Okay. So now we're going to grab a button from either our kits or Fritzing or whatever. And it's going to bring up a whole bunch of buttons. Momentary switch and a push button. We're going to use the generic push button. I'm going to drag it down, and I'm going to rotate it 90 degrees. You might be like, well, why did you rotate it 90 degrees? Well, I'll tell you. So basically the way buttons work in electronics is they basically either break or complete a circuit that's going through these terminals. But the interesting thing about it is, let me go ahead and bring the pen up. Either side of the button, pink is not really visible. Let me try blue. Yeah, that's better. Either side of the button is always connected. So if you hook something up to the top terminal, the bottom terminal will always be receiving power from the top terminal. More than likely, if it's anything like the Arduino events, there will actually be printouts of circuits, maybe using Fritzing, but you would, for like the troubleshooting part, you would be looking at printouts of circuits as opposed to working with actual circuits. Now, the thing about the Arduino event is there's a troubleshooting part where you work with that printout stuff and you do like multiple choice or something like that. And then there was a building aspect where they actually built using physical, Arduinos and breadboards and electrical components and things like that. This is a different event from that, and this is relatively new compared to that Arduino event as well. I mean, both events are fairly new, but the Arduino one has been around for longer. I could not tell you for certain whether or not there will be a circuit building part. I know that there should at least be a troubleshooting part, and then that will more than likely be with printouts of circuits and things like that, like diagrams of them, much like you would be looking at here. Middle school has both Raspberry and Arduino circuits. No, this is just Raspberry Pi. I mean, there might be a middle school Arduino event, but this specific one that you guys are working with right now is just going to be Raspberry Pi. There are separate events, though, that use Arduino. But yeah, you guys will just be working with Raspberry Pi. But yeah, so buttons. Will I share any previous year's sample tests? I don't have any to share, unfortunately. Hopefully, Mr. Dubik will be able to hopefully Mr. Dubik will be able to provide some, but again, this is a very new event, so I'm not even sure if there are sample tests or uh, questions from previous year's events. But I will, if I ever come across that information, I'm going to ask Mr. Dubik about it again. If I ever, if we ever happen to get a handle on that situation, I'll be sure to share that with you guys. I won't leave you guys out in the dark, definitely. No, no, I apologize. I'm not Mr. Dubik. I just have his name for this because that's what it was originally set up for. No, I'm Mr. Toy. Yeah, periodically Mr. Dubik pops in here and he you guys recognize that because then he comes in and then you've got two people talking and no, it's been well, what can I say? I just like to confuse people. I am it's what I live for. It's just is muddling everything. But yeah, so back to the thing at hand. Buttons. The top terminal is always connected to the bottom terminal on buttons. You see how I have it rotated, where both terminals are sticking out to either side. So the left-hand side has two terminals and the right-hand side has two terminals. And let me just go ahead and erase the drawings again. So this top terminal right here is always connected to this bottom terminal, no matter what, whether or not the button is being pressed. Always, always, always connected. However, there is no connection across the button. None whatsoever. This terminal is not connected to this terminal unless, or nor is it connected to this terminal, unless the button is held down. For as long as the button is held down, then this terminal is connected to this terminal and this terminal is also connected to this terminal, and it goes the other way. So this terminal is connected to this terminal, and this terminal, and this terminal is connected to this terminal, and this terminal. How many times can I say terminal and circle those little metal bits on there? But yeah, electrical connections will stay on the same side unless the button is being held down, in which case it will complete the circuit over to the other side. So with that in mind, let's go ahead and hook up our button. So I'm going to hook it up so that the top of the button, the top of the button is at 9E and 9F. And the bottom of the button is at 11E and 11F. So as you can see, we've got pin 1. And if you mouse over it in Fritzing 2, it says pin 1 is always connected with pin 2. Huh. This is actually a sideways button from how they normally work. So let me go ahead and rotate it then. We can't rotate it. This is very different from how push buttons normally work. Normally they don't jump across to the other side unless the button's being held down, but we'll just adjust for this. So yeah. Normally they're not connected on the opposite sides, but in this case it's a little bit different. So pin 1 is always connected to pin 2. This is pin 2 over here in 9F. And then we've got pin 3 is always connected with pin 4, and they're in E11 and F11 respectively. So not the end of the world. We can adjust to compensate for that, but just keep in mind that that's a little bit unusual as far as this is concerned. So we're going to connect GPIO 18. Rather, let's connect GPIO 27. We're going to connect GPIO 27 to pin 1. We'll go ahead and make that one yellow because that'll be our input pin. So I've got GPIO 27 hooked up to A11. it is on the same rail as pin 1. Then, yep, that makes sense. Then we're going to connect the power rail to pin 3 on the push button. So we're going to get a jumper cable running from the power rail to A11. So you remember what I was saying about how normally the button doesn't cross, doesn't complete a circuit across, and how this one works a little bit different? This one, it doesn't complete a circuit from top to bottom unless the button's being held down. So what we're doing here is we're having electricity travel across. Normally it's going to go across and then into, you know, the end of the circuit over here. We're going to complete the circuit over here. However, whenever the button is held down, instead electricity is going to travel up and across this terminal into the Raspberry Pi, thus completing the circuit that way. And that's how the Raspberry Pi is going to be able to take in a signal and recognize that there is something there. Now, I don't have it technically a complete circuit there. I guess technically you don't need one, but for just sort of good electronics, best electronics practices, I'm going to grab another resistor. And we're going to make this resistor, let's say 10,000 ohms. I cannot do more than 100. 999. Let's make it 5. Can we do 10,000? No, we can't. Oh, can you use K? You can totally use K. So 10K. Make this a 10K resistor. Back to a 4-band. Yep, that is totally a 10K resistor. Hey, that's pretty useful. So we're going to make this a 10K resistor. It's 10,000 ohms. And we're going to plug it in from J11 to the ground rail on this side. Now, stay with me here. We're actually going to connect the ground rails across the breadboard. So down here along the bottom, what I'm going to do, oh my gosh, work with me. Work with me. There we go. So I'm going to connect 2 ground rails together. And again, this is just for cleanliness purpose. It's not actually technically useful. Okay, so what I've done here is I've actually connected this ground rail to this ground rail over on this side. So now this is all one long ground rail and everything's hooked up. And that's hooked up to the ground on the Raspberry Pi. You don't, strictly speaking, have to do this. So if you don't have like a 10,000 ohm resistor, don't worry about it. But this is just so that there's always a complete circuit. The 10,000 ohm resistor is there because, so as we've learned from looking at this, pin 3 is always connected with pin 4, right? So this circuit across the button always exists. This is 10,000 ohms. So it has a lot of resistance on it, which also helps to reduce the amount of power that's going back into the ground on the Raspberry Pi, blah, 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 on a regular basis. Now we hold down the button, and the electricity has a choice. It can either travel upwards along the button into the internals of the Raspberry Pi to produce a signal, or it could continue going the path that it always goes. So one of the reasons why we're doing this is to encourage the electricity to travel down this pathway whenever the button's held down. So we know that electricity always travels the path of least resistance, right? So we want to make sure that the electricity is going to travel up the input whenever the button's held down. So we put this here so that the circuit's always complete, even when the button's not being held down, but whenever it is, it's going to change path to go down the Raspberry Pi input. And there we go. That's actually the circuit that we need in order to work with our inputs. So I'm going to go ahead and close down, well, I'm going to move fritzing over here so that you guys can spend time looking at the circuit in case you want to, you know, double check it against like your own. Let's do this. No, that's way too big. Hold on. There we go. I'll actually zoom in a little bit. Try and provide a complete picture of the circuit here. There we go. All right, so the circuit is complete, and now we work on the programming aspect of it, which is going to be a more important part of it anyway. I think it's going to be more directly related to what you guys are going to be working on with the Raspberry Pi anyway. So let's go ahead and spend a little bit more time working on the Raspberry Pi programming aspect than we did on the circuit building aspect. Okay, so if we go back to the the Raspberry Pi Scratch like we did last time, again, I can really only show you in slides, unfortunately. Remember those broadcast messages I was talking about, that we were talking about, and why you might want them? Well, remember we need those in order to turn on the GPIO pins and configure them to be output. Well, one of them needs to be output. One of them needs to be input. So we're going to set GPIO server on, a broadcast message for GPIO server on, and a broadcast for config 17 out, which is going to set GPIO pin 17, which is pin 11, to be an output pin. So far, none of this is new stuff. However, we're going to add another one. It's going to be config 18 in pull down. It doesn't actually, I see what they did here. Okay. If you're building a physical circuit, I want you to go back real quick and change something on it. If you're working with fritzing, don't worry about it, just understand that sometimes I'm wrong. So if you're working with a physical Raspberry Pi, I want you to get rid of that 10,000 ohm resistor that I had you hook up before. That's going to mess with things if we end up using a pull-down resistor. Yeah, it has a built-in pull-up resistor. It has a couple, I believe, of voltage regulators that can basically make one of the, like that can essentially enable pull-down resistors for the GPIO pins. It's pretty versatile in that way, but then on the other hand, I probably should have realized that they were using the pull-down resistors. So if you can keep actually this ground connection across the two ground rails if you want, just as long as you get rid of that resistor. Because honestly, this doesn't really change a whole lot of anything. It just makes both of these ground rails, but if there's nothing hooked up to this rightmost ground rail, nothing's changed. So yeah, just pull out the resistor from the circuit, at least for now, because we're going to be using resistors on the Raspberry Pi, built into the Raspberry Pi. So yeah, this is going to be a third broadcast message that is config 18 in pull down, all one word. And this is actually two commands, or it's one command but with a special option attached to it. So config 18 in is configuring GPIO. Well, you don't actually want config 18. You want config 27 in. Sorry, apparently I'm all out of sorts today. So you want config 27 in pull down. Definitely want 27 if you hooked it up the way I did, because I had you guys hook it up to GPIO 27, not GPIO 18, because that one was sort of in the GPIO 17, and the wire that connects to it was sort of in the way of GPIO 18. So in order to make it visible, I moved the connection over to GPIO 27. So we want this to be config 27 in pull down. What that's doing is that's configuring pin 20, GPIO pin 27 to be inputs, and then using the pull down resistor setup that's inside of it. And then go ahead and add your forever loop just like before. And again, remember, because all of this setup stuff really only needs to be done once. Make this a little bit more beautifuler. There, it looks a little less unfortunate. I feel like a little less squished. So yeah, this stuff up here really only needs to be placed once because it's set up. So the one green flag clicked and the broadcast GPIO servers on, or GPIO server on, and config 17 out, and config 27. 20. Hello. Yeah, config 27 in pull down, and then we go into our forever loop. We're going to throw an if statement into that forever loop. How many of you, by show of hands, are familiar with if statements? Okay, we got a couple of hands. Not many, though. Most of the hands are not up. And that's fine. There's actually nothing wrong with that. You don't know something if you've never exposed to it before. So let me tell you about if statements. So in programming, 27, config 27 in. Sorry, yeah, it's confusing because the screenshots are for a different setup, but it's config 27 in pull down and config 17 out. I like to think that in programming there are three. So like all of the, this is sort of a false analogy, but it's one that can be kind of helpful to, I don't know, kind of make sense of everything, at least in my head. Of all of the colors that exist on the spectrum, there are three primary colors, right? There's red, there's blue, and there's yellow. Everything else is some combination of those three colors. Or if you're working with computers, there's red, there's green, and there's blue, and every color is a combination of those three colors. There are sort of, yeah. So I like to think of three concepts in computer science that are sort of the primary colors of programming that everything else is built off of. And they're variables, they're loops, and they're control flow. So variables and loops, we've already, at least to some extent, exposed ourselves to. Variables hold things, loops repeat bits of code over and over again. Control flow changes how your program operates based on its own status. What do I mean by that? Well, okay, so like let's say let's say how you get ready for school each morning is considered, or get ready to go out the door for whatever. You could be going to the store, you could be going to, I don't know, fencing practice, you could be going to school, you could be going to track, whatever. How you get ready in the morning each morning is a program. So far, we've been working without control flow. So you can think of the program that runs this getting ready for the morning being, wake up, put on shirt, put on pants, put on shoes, have breakfast, go outdoor. Greatly simplified, but you can kind of think of it like that. And it's definitely put on shirt as in t-shirt and put on pants as in jeans. If you're anything like me, it's, t-shirt and jeans every day, all day. But sometimes, yeah, exactly. Sometimes it's raining. Sometimes it's snowing. Sometimes it's nighttime. Sometimes it's really super bright. Sometimes it's hot. Sometimes it's cold. The days aren't the same. So if we had this program in our lives of getting ready and doing the thing, yeah, exactly, Ved. There would be situations in which our program, that is our way of getting ready in the morning, would not produce, desirable results. We'd be walking out into the middle of a huge thunderstorm wearing a t-shirt and jeans and I don't know, flip-flops or something. Or you'd be walking out into like the greatest blizzard North Carolina's ever seen in a t-shirt and jeans. Or it'd be this record heat wave and you're wearing a t-shirt, which is okay, and jeans, which is ugh. So control flow allows us to evaluate the state of the program. Yeah, I kind of would too, but at least try to, dress for the weather nowadays. Control flow allows us to evaluate the state of the program and change what it does based on that. And it's done with these if statements are the most basic example of control flow. So instead of just this regular program that runs the same every day, why don't we throw in something else? We'll say, if raining, grab umbrella. If snowing, grab coat and boots. If sunny, grab sunglasses. If hot, wear shorts instead of jeans, that kind of thing. And so you could run through these things and run one bit instead of another bit. So like if you wanted to, if you wanted to account for the fact that it's a hot day, if it is in fact a hot day, then you would be wearing shorts instead of jeans and probably sunglasses as well, because more than likely it's also very sunny. If it was snowing outside, you'd be also wearing a winter coat and boots and things like that. If it was raining, you'd also grab an umbrella. Like those if statements would execute. And they're basically structured like so. They're very simple in regular programming terms. It's just if statement code to run if statement is true. Now, these types of control flow are called if statements. The key word is if. And then you got the stuff in parentheses. Yeah, basically. So if whatever is inside the parentheses is true, so if weather equals raining, or if, I don't know, score is greater than 5, or if day of the week equals Wednesday, whatever. If whatever's inside of these parentheses is true, then the stuff basically inside of the if block will run, the if statement block. If it's not true, so today is in fact Tuesday, it's not Wednesday, this code is ignored. You just skip the block and you move on to whatever's next. So that's what we're doing here. We're putting an if statement inside of a forever loop. If whatever we have in the conditional here is true, yeah, essentially if button pressed, then we will execute whatever's inside of the if statement. Otherwise, we'll ignore it and just run the rest of the code. Yeah, you got the idea of it. Exactly. So in this case, we would want to test and make sure that the button is being held down, because if the button is held down, then we're receiving inputs on GPIO 27. So we can go to operators, and as you can see, there is this special set of operators here. And what these are specifically for conditionals, if statements, checking to make sure whether or not something is true. So you can use the equals one, and in the first or the second block here, you can just put in 1. Yeah, select operation, then the equal comparison, and then finally set it to 1. And then you would run the program once. It won't do anything, but it will actually, by setting it up, it will turn on the GPIO pins and configure pin 27, GPIO pin 27, to be input with pull-down resistance. Then once you've run the program once, just go ahead and stop running it, and then go to sensing. Then you go to slider sensor value. And the slider sensor value is actually a drop-down menu. If you click on it, you'll see that GPIO 27 will become one of the options. And part of that has to do with the fact that you guys ran the program once and sort of jogged the Raspberry Pi's memory and internals to think that GPIO pin 27 was a valid option for sensor value. So if you click that little drop-down menu, you should see GPIO 27, not GPIO 18. Excuse me. Go ahead and drop it into the first part of that operation. So now we're asking if GPIO 27 sensor value is equal to 1. I imagine you guys probably know what's going to be going from where we're going to go from this point. For now, though, we're going to go ahead and call it a day. Yeah, exactly. Broadcast GPIO 17 on. I actually probably shouldn't leave you guys in suspense there. Broadcast GPIO 17 on. That will turn the LED on whenever you press the button. However, we're going to take a break from the coding for now so we can do the poll questions and the question and answer time so I can get ready in time for the Arduino version of this. But I do want to ask this question. The code will operate strangely. What will the LED not do? How do you think this code will run so far? It will turn on. It should turn on. Exactly. The LED will turn on once, but will never turn off. Oh, there you go. That would do it. But yeah, the LED will turn on once, and it will never turn off because we haven't told it to turn off. So the LED will stay off until you press the button, and then it'll turn on and never turn off again. So yes, let's go ahead and do the poll questions, and then we'll do question and answer time, and we'll break for the next couple of days, and we'll meet up again on Thursday, and that should be, I believe, our last time meeting up. So let me go ahead and get started with that. Yeah, I know. So here we go, first question. Oh, and let me go ahead and